Thank you for coming to this event, and I hope it's enjoyable to all of you for the next several days. My name is Chris Monroe, and I sort of have two jobs as a faculty member at Duke University and a director of the Duke Quantum Center, and also as a co-founder and chief scientist at IonQ. Of course, IonQ is helping sponsor this event, and Jungsang Kim will speak right after me. You won't hear the same talk. You'll see two different sides of a coin. I suppose I will start off more foundationally and give a short overview of the field of quantum computing, defining things. And I know many of you are already experts in the field. Some of you are experts in some field, but it might not be quantum, and that's the perfect audience. So I'll start by defining what a quantum computer is and how it deals with information in different ways than what we're used to in conventional or classical computing. So the history of classical computing and classical information is actually not that old. As you know, in the early to mid 20th century, fellows like Alan Turing and Claude Shannon applied the mathematics of information theory to the idea of what computing is. And their work, they were both, they were not computer builders per se, but their contributions in the field are very important because they abstract the idea of information to pertain to almost any device that can store bits. And a bit is just a two-level system, something that has two positions, on and off. And you can, of course, store information in higher level logic than bits. You can use tertiary logic, four-level logic, and so forth. We were just talking over lunch about that. But bits are sufficient, and in nature they're found all over the place. I'll talk about that in a minute. But Turing, you know the concept of a Turing machine. Again, he didn't build one of these things. I don't think anybody really has. But it's an abstract machine that has a tape and a read-write device and memory. And the idea is you can compute anything if you have sufficient size tape with zeros and ones, and you can switch those zeros and ones depending on the state of your memory. So this is like a head and a tape model of a computer. And that turns out to be a universal device. It can compute anything. And again, it's abstract, but it's very important. Now, we don't build machines exactly like this, but they can be mathematically modeled in this way. And that was an important development because it gave scientists and engineers an opportunity to look for bits and try to build machines based on that model. Now, Claude Shannon, I think, maybe more mathematically invented what information is mathematically in terms of bits. And maybe you've seen this formula. It has to do with the information content in a distribution of letters picked from some alphabet with probabilities. So it has this interesting form. And the important thing here is that bits are really where we need to look in terms of computing. And back then in the mid 20th century, we had these vacuum tube computers. You've seen these pictures. These are the Brits seem to be always first when it came to computing. That's largely due to Alan Turing, but Colossus. In the United States, we had ENIAC, and this is actually the Soviet Union, something called MESM, in the late 1940s, and they were all copies of the same thing. These were vacuum tube computers, and the heart of these devices, the heart was a set of vacuum tubes. These were the bits. They stored two levels, and they can be wired together in a way that allows you to compute. Now, this sort of vacuum tube model of a computer, I mean, these computers worked, but they required thousands of these vacuum tubes, and they failed. They were worse than light bulbs. They failed a lot, and they were very unreliable. And so, going back to Turing, though, and Shannon, you don't need vacuum tubes if you can find maybe a better device. And, of course, the better device that came along in the 40s was a solid-state transistor. This doesn't look any better. The very famous picture of the first solid-state transistor, it's a germanium semiconductor with a gold point contact, and it has three terminals. You can sort of see one here, and one here. Sorry, one here, and one there. And this is basically an electronic switch. It didn't involve vacuum tubes, but in fact, this by itself was more of a physics experiment than the vacuum tube, which this is clearly, at least you can make these things and you can manufacture them. But this was 1947 when it was a physics experiment, and of course, in the following few decades, we were able to fit billions of these effective semiconductor transistors on a single chip. And that was, of course, the advance of very large-scale integration that really took off in the 70s, I would say, 60s and 70s and 80s and 90s. And with VLSI, we're all familiar with Moore's Law, and there's a point to this history that's going to lead into quantum, and I'm getting to it right now. Now, Moore's Law, as you probably know, is a statement that, well, you can't read too much here on what's going on. This is the number of transistors on a given CPU chip over time, and you've probably heard it expressed as the number of transistors doubles every couple of years. And that's what this plot is. This is a logarithmic plot here. So it goes up by a factor of 10 almost every decade, something like that. And what you'll notice on this plot, this is scaled to 1978, so that's why it's 1. You'll notice on this plot, in the last decade or so, it's tapering off, and we recognize this. It gets really hard to make transistors much smaller than about 10 nanometers. They're getting down there, but when you get below 1 nanometer, people don't really know how to do this. There will be all kinds of issues involving the granularity of materials, the individual atoms, and actually there are quantum effects that creep up there. So there's a problem in the scaling of Moore's Law to keep continuing this way throughout the 21st century, and it almost certainly won't. So now I want to go back in time once again to this remarkable lecture and prediction of Richard Feynman, and this is from 1959. And I think he was a physicist, as you might know, very colorful character who he liked to tinker. He was a theorist who got a Nobel Prize in describing the quantum mechanics of the electromagnetic field, but he liked to tinker. He liked to play around with models, and he was very interested in technology. And he was very excited in the solid-state transistor because he knew that it could be shrunk down. In 1959, he knew that it could be shrunk down to really small sizes. And so in this lecture of his called "There's Plenty of Room at the Bottom," meaning that you can shrink things down and it can get very powerful, he has this amazing quotation. He says, "When we get down to circuits, maybe transistors that only have a few atoms in them," he said there are new opportunities for design. For he means design of computers. And the reason he's confident of this is that when you get down to a few atoms, there's a whole new law of physics that takes over, the laws of quantum physics. And this is the opportunity that Feynman predicted. Of course, at the time, he didn't know what this opportunity meant. Nobody really did at the time. And I think now we do, starting in the 1990s, that this opportunity is called quantum computing. So with that, I want to talk about these laws of quantum physics. If you've never had a quantum physics course, it's okay. It's actually not hard to explain what it is. And the way I think of quantum physics, in fact, I teach it this way to students that have never seen it before. Quantum physics has exactly 2 laws, and they're actually very simple to state. And I'm going to go through them. I call them the golden rules of quantum mechanics. There's just 2 of them. Now, the first one, it might sound strange, but quantum objects, the quantum description of matter, requires us to think of matter as behaving like a wave. And what does it mean to have a quantum system? It means that it's very simple. Often it means you're at the atomic level or even the subatomic level, individual fundamental particles. But mainly you need to have a system that's very simple. It doesn't have very many degrees of freedom to move around. And when you have a system like that, and it's isolated, I'll get to that in a minute, it behaves like a wave, and one property of a wave that conveys to a quantum system is that it can be in superposition. And so when we apply this to information, we're of course going to try to extend the concept of a bit to something we call a qubit, a quantum bit. So unlike a bit, a quantum bit can be in both states 0 and 1 at the same time. So if you haven't seen this, this is just jargon. It's a mathematical language we use to describe quantum states. This funny line and the angle, that's called Dirac notation. Paul Dirac invented it. It's a shorthand notation. It just means we have a quantum state of some system, and it has both 0 and 1. Now, these are very abstract labels. This could be the on and off electronic switch. It could be two states of an electron orbiting a single proton in this hydrogen atom. And they're interesting parameters, A and B. These are continuous numbers that correspond to the weights of how much 0 and how much 1 there is. And this plus sign, finally, the last symbol, it's not the usual plus sign. It just means we're superposing both 0 and 1. Now, waves are like that. Waves allow for multiple states at the same time. Like when you hear two musical notes, you're hearing your eardrums vibrating at two frequencies at the same time. And one can be louder than the other, for instance. So the idea of rule number 1 is that we have to admit that matter or any quantum system can be in a state of superposition. And when applied to data, we now have the ability to store a bit in both 0 and 1 at the same time. Okay? Now, where's the math here? You've probably heard, well, quantum, the math is too hard. The math in quantum is, it's not trivial, but it's no harder than math you've seen before in other types of wave mechanics. So this is called the Schrödinger equation. It tells you how this system evolves in time when we control it in a certain way. And basically, they're differential equations. A and B get to change if we push the system according to this operator. It's called a Hamiltonian. It's our controls. This is how we control a quantum system. And it can oscillate back and forth between 0 and 1, or it can be 50-50, and we can manipulate things that way. So this is math. It's not particularly hard. In fact, it's a lot easier than the math that describes water waves. These are nonlinear differential. At least the Schrödinger equation is linear. The equation that describes this wave here, a surface wave, is highly nonlinear. It's very hard to solve, much more difficult than the quantum mathematics. So if you say the math behind quantum is so hard, well, you must admit that it's easier than solving this problem in a certain way. I'll maybe expand on that in a minute. Okay, what about rule number 2? Well, there's rule number 1, and the problem with rule number 1 is that we never experience things in two states at the same time. What does that mean? I mean, this remote control can be in two places at the same time, I guess, if it's a qubit. So there's a problem with that. We have to reconcile it with our everyday world, and this is why we have to make rule number 2, unfortunately. And to me, rule number 2 is the weird one. Rule number 1, it might have some math, but there's nothing really strange there. It's rule number 2 that's strange. And this is a little bit of a joke, but rule number 2 basically says that first rule works only when you're not looking, only when you're not observing. And so therefore, no problem. We have a superposition. It exists as long as you don't look. But what happens when you do look? Well, when you do look, this superposition, it snaps into a definite state of existence, which is good because that's all we experience in life, definite states of things. We don't see superpositions. And you might not be surprised that there's a probabilistic interpretation here of rule number 2, and basically it snaps into one or the other state with a probability that's given by A and B. A and B are actually complex numbers, and you have to square them. That's sort of bookkeeping. Don't worry about that. The point is that the weight of the superposition is related to the probability you will see that particular state, okay? Now, to me, the single weirdest thing of quantum physics is that we have to use probabilities. Where did they come from? So everybody uses probabilities in all walks of science and engineering and mathematics, and it always, with one exception, probabilities are always an expression of ignorance. Like the weather, it's going to be 50%, there's a 50% chance it'll rain. Or when you flip a coin, it's an evenly weighted coin, should give you a 50-50 probability, just because we didn't bother to calculate all the details. Maybe it's very hard to do that. In the case of weather, it's probably not impossible, but it's just, the problem is super hard because we have to model all the little pockets of air in the atmosphere and so forth. So where do these probabilities come from? In quantum mechanics, it's not about ignorance. And that's the weird thing. They just sort of come out of the woodwork. They come out of thin air, these probabilities. Einstein famously said, God does not use dice. And he did not like quantum mechanics, and most of us don't like quantum mechanics because of this. But this is the way the theory works. It's been tested more accurately than all other theories in all of nature. So it's here to stay. And moreover, if something does replace it, it's going to be at least as weird. So this is quantum. That's it. And there's very little math that we needed here. I mean, yes, you need the math to understand how A and B change. And that's going to play a role in building a quantum computer because we need to control A and B of lots of bits. But this is it. If somebody tells you, oh, quantum is just way too hard, I can't understand it, well, you're in good company because nobody can understand it, I would claim. And if they claim they understand it, they're missing something. Conceptually, it's very strange. Okay. So moving on, I want to now tell you the story of quantum computing. We're obviously going to put a lot of bits together. And I think of it as a good news, good news story. When you do this, let me just go through what I mean here. So the first thing, when you put lots of qubits together, there are lots of possibilities. In fact, there are exponentially many possibilities. With 3 qubits, there are 8 possible 3-bit states. And so I've illustrated in this black box, we have 8 inputs. And we're going to compute something on those. I'll tell you what that means in a minute. And we're going to get 8 outputs, all in parallel. It's all one device. It's like parallel processing, but with one device. That's really good news. And this is, by the way, this is a quantum state of 3 qubits. It's the most general arbitrary quantum state, and it has 8 weights, because there are 8 possibilities here. There is a constraint. The probabilities all add to 1, but that's just one constraint. We have exponentially many weights. And the power here, let's see, I think I might be getting ahead of myself. One thing that's very interesting here, if you look at this state here, if I flip the first bit from 0 to 1 and 1 to 0, what I'm doing is I'm shuffling these two, A0 and A4. I'm swapping A1 and A5, A2 and A6, A3 and A7. By flipping one bit, there's, in a sense, 4 swaps happening. And that also scales exponentially. 8's not very big. But if I give you 300 qubits, that's a huge number of possibilities. I can't even begin to write down all of them. 2 to the 300, that's a lot. That's 10 to the 90 or so. There's not enough space in the universe to even write all those things down. Nevertheless, if you flip just one of those 300 bits, you've performed almost 2 to the 300 swaps. So this is really the power of quantum computing. You get wiring for free. And I want to explain that the buzzword behind this is called entanglement, and I want to tell you a little bit about that. So this is great news. It sounds like we can compute massively in parallel ways, super fast compared to any problem a classical computer could do. Even with 300 qubits, we can compute over a space that we'll never, ever compute using classical computing because there's not enough matter in the universe to even store 2 to the 300 pieces of information. Okay, that's the gain of exponential. That's the good news. The bad news is that you need to measure this output. And when you measure a quantum output, especially one that has lots of qubits, you only get one answer. You may have computed 2 to the power 300 answers, but you only get one, and you don't know which one you get because it's probabilistic. So it's almost as though you're just going to measure noise. So this is really bad news, and I'm sure Feynman realized this, in 1949 when he gave that speech, and it sat that way for many decades. Until the mid-90s, early 90s, I would say. There were hints of it in the 80s, but the idea is there's a final piece of good news, and it has to do with what happens in this box. Before you measure, we can take advantage of wave-like interference of the qubits by pushing the quantum state around in a certain way. As I mentioned, there is math involved with that. We have to control these quantum bits in such a way that there are interferences that occur. Waves interfere. Waves can cancel each other out. They can reinforce each other. And you can imagine there are computations where not just 8 inputs, but 2 to the 300 inputs, they almost all cancel out, leaving just one answer at the end, and all the others have 0 weight. So if you measure them, you're never going to see them. And this is nice because when you measure this, there's no probability anymore. You're going to get with a probability nearly 1 that you get this state. And that state that you measure, it can pertain to all of the inputs. Now, I'm speaking very vaguely, because this is a very high-level version of a quantum algorithm. It's not obvious what algorithms can be cast in this form so that you get that massive interference. That's an open question. It's not clear, partly because we don't have big quantum computers yet to play with. But there are very likely, there's at least a few class of problems that can be put in this form. And I'll talk a little bit about that. What are these orange dots? These are what we call quantum gates. These are the ways that we manipulate quantum states to get them to interfere. And by using the language of quantum gates, we borrow from classical computing, where we also have gates that are universal and they allow us to compute. All those transistors on that big, on a CMOS chip, are wired up in a very certain way to make gates. This is the typical universal classical gate. It's a NAND gate, and you get that by simply stacking 2 transistors in a cascade like this, and you can clearly see that the output is the NAND of the 2 inputs, and you get this truth table. And that's universal. If you can apply NAND to any 2 bits in a classical machine, you can pretty much do everything. You can make adders, multipliers, and everything else you need. Now, it turns out there are a universal set of quantum gates. And this was a lot of work in the 1990s, showing how we need to build these things, and we have to understand a model for having a quantum computer operate. And so the gate model is the one that's out there that we know can work if we can realize gates. So these are interesting gates. Even a single qubit gate's kind of interesting. You know what a NOT gate is in classical logic, just 0 to 1 and 1 to 0. But in quantum logic, we can do more than that. We can, in a sense, halfway do a NOT gate. We call it the square root of NOT. It's the operation which, when applied twice, gives you a NOT gate. Well, classically, that's nonsense. Classically, all you can do to a single bit is leave it alone or flip it. And if you do that twice, you end up at the same state you started with. Okay? So it makes no sense that there can exist a square root of NOT gate in classical logic. But in quantum logic, there does. And here's an example. If 0 goes to a superposition of 0 plus 1, and by the way, remember I said the weights are complex? They can have a sign to them as well. And that's really important for kind of technical reasons. And remember, the probabilities are squared, so don't worry about the minus signs. But the minus signs are important because if you do this operation twice, if you do the same operation twice, you can see that 0 goes to 1, and 1 goes to 0. So that operation must be the square root of NOT. So it's one of a family of single qubit gates that we use. The general ones are called rotation gates. You can rotate between 0 and 1 any weight you want, and that's going to be an interesting and useful gate for algorithms. Now, the other gate that's maybe more interesting for a reason I'll tell you in a minute, but it's also typically the bottleneck, the hardest thing to do in a quantum computer. We need a 2-qubit gate, sort of like the NAND gate that we had with universal logic. We need the qubits to interact. That way we can spread around information and make these big superpositions. Now, this is called the controlled NOT gate or the quantum exclusive OR. And you're basically taking 2 inputs and you get 2 outputs. The first input is the first output is the same as the first input. The second output is the sum of the first of the 2 input bits, modulo 2. So it's the XOR, if you want. Another way to say it is an XOR gate flips the second bit if and only if the first bit is 1. So that's one example of a universal 2-qubit gate. And you can see that it's useful to make something called entanglement. I'll tell you what that is in a sec. But if we have a superposition of the blue qubit and the red qubit as the input to an XOR gate, we end up with 0, 0 remains 0, 0, but 1, 0 becomes 1, 1. So we end up with this funny superposition, 0, 0 plus 1, 1. It doesn't look very funny. That's a pretty simple superposition. It's called entangled because you can't separate this into the blue system and the red system. They're entangled. They're inextricably linked. It's this linkage that are the hidden wires I spoke of earlier. When you flip one bit, it sort of flips exponentially. It can flip exponentially many amplitudes, many weights of the quantum system. So entanglement is an important resource, and you need 2-qubit gates to realize it. Okay, so let's go a really high level now, and what can you do with these things? I mentioned the 1990s were a very important time in this field, and it's largely due to a man named Peter Shor, who showed that a quantum computer can factor numbers exponentially faster than any known classical algorithm. So factoring is the inverse of multiplication. For small numbers, we memorize things. It's easy, but even for this number, your computer can factor it into primes pretty fast. But if I give you a number with, I don't know, 500 digits, it turns out that this will take the age of the universe or something like that. It's a long time to factor. It's probably many times the age of the universe. And the reason is factoring gets, every time you add a digit, it gets roughly twice as hard. And so add enough digits and it becomes impossibly hard. And the reason factoring is so important is, of course, because the inability of factoring large numbers is why most public key encryption standards work. So it's a very important application. And so this is sort of math behind the best classical algorithm for factoring is exponential, actually in the cube root of the number of bits. So every time you add a digit in base 10, it gets about twice as hard. But Shor's algorithm showed that the complexity of factoring is now only polynomial. It only goes like n squared times some prefactor. Okay? So this changes the complexity of a problem from hard to easy in math speak. So the way Shor's algorithm works, this is really hand-wavy, I apologize. I showed this slide, actually Peter Shor at MIT was in the front row, and I was really embarrassed giving this talk. So this is Shor's algorithm. Let's say we want to factor the number 39. Well, 39, it takes at least 6 bits to represent 39. So we need 6 bits. Did I get that right? Yeah, 2 to the 6 is 64. And let's say we make a superposition of the first 39 numbers in binary. You can do that with 6 bits. And I'm not going through the secret here, but it's not a secret. Shor showed how you can massage this quantum state with gates, and not too many gates. It only scales quadratically with the number of bits. You apply gates until the quantum state becomes this, a superposition of 3 and 13. And then when you measure it, you're going to get one of the factors of 39. That's basically how it works. Now, unfortunately, to factor a number that's truly interesting will require more than 6 bits. It'll require probably 1 million, maybe more. This estimate goes up and down depending, but it will probably require tens or maybe even a billion, tens of millions of gates or maybe 1 billion gates. So we don't have machines yet that can even touch this problem. However, there are other application spaces, and Jungsang will talk about this in more depth, in some real machines we're building at IonQ, that look much easier, but unlike Shor's algorithm, they're not provable. These are largely heuristics. So what we look for in a quantum algorithm is something where the answer depends on all of the inputs. So an optimization type of problem is an excellent target because the optimum output of some function is a single value, and it depends on all of the inputs and all of the functional evaluations of those inputs. So you could imagine it's possible that a quantum algorithm could somehow do the interference right and get you the answer in the end. And an example of an optimization problem, a trivial one, is identifying the tallest peak in this landscape, which is easy because it's a two-dimensional space and you can map it and just look. But if you have an n-dimensional space, you can't plot it and it becomes really hard. The traveling salesman problem is a very well-known optimization problem. Again, it's a combinatorial optimization problem. You remember the traveling salesman problem asks you to find the shortest path between n places on a map, visiting each place exactly once. And there are too many possibilities, and it's very hard to find the optimum. In fact, a quantum computer probably can't solve this problem. We don't believe it can, but it may be a heuristic that can solve an approximation of this problem better than any classical computer could. So it's heuristic in that we probably can't prove it, but if we get a better answer, that's easy to prove that it's better than any classical optimization could do. Molecular simulations, again, I think Jungsang, you'll hear much more this week about quantum chemistry using quantum computers. The way I think about it is that even in small molecules, if there are a few hundred electrons, those few hundred electrons interact in a very complex way, and there are way too many configurations to consider of all the electron orbitals to find even the ground state of that molecule, the equilibrium state, much less the dynamical behavior of that molecule. So using quantum computers to encode molecular wave functions is a very important field, and again, you'll hear much more about that this week. Okay, now that I'm more than halfway through, I wanted to talk about implementations. Well, this is a line from my friend Bill Phillips, a Nobel laureate friend of mine from the University of Maryland and NIST, and he's fond of saying that a quantum computer is more different to your laptop than your laptop is from an abacus. And what he means is that the laptop and the abacus are both Turing machines. You can model their information processing characteristics with a Turing machine and bits and so forth. These two, not so. They use information in totally different ways. And so to me, the corollary to this statement is that why would we ever expect a quantum computer to look anything like that laptop? I mean, the laptop doesn't look much like an abacus, but it kind of is an abacus. So to build a quantum computer, we have to really think outside the box with different systems, and they probably won't. As a hint, I don't believe quantum computers will be built out of solid-state materials. And I'll explain that in a minute. So this is a slide that I stole from Science magazine about 7 years ago. It was just a review article that the editors wrote summarizing all the technologies out there for good qubits and building a quantum computer. And so these are all exotic in their own way. And I like to break them out into the 4 on the right and the 3 on the left. And there's probably a few more you could add in here. The 4 on the right are so-called synthetic qubits. These are qubits that are man-made. They have to be held at nearly absolute zero. They're usually solid state. That's why they have to be so cold, because in solid state you have thermal reservoirs. You lack that isolation. Remember rule number 2, you can't look while you're doing the computation. Well, if you have a thermal bath, it's looking. It's interacting with the qubits. So superconducting loops are probably the most advanced that have been built into systems. There are silicon spins that people have put a few qubits together, but it doesn't look, nobody really knows how to scale. In fact, nobody really knows how to scale any of these things. I think there's a lot of physics needed. On the left-hand side, these are what I call natural qubits. Now, natural qubits are already quantum. In some sense, their environments don't have to be cold. These are individual atoms, electrons, photons, ions, molecules, things that are given to us already. And I would say of the natural qubits, trapped atomic ions are the most advanced technology right now that have been built into systems. Neutral atoms are coming on hard right now, but they're maybe a decade or more behind the trapped ion systems, and I'll tell you why in a bit. But I'm going to clearly talk about trapped ions, and you're going to hear a lot about them this week. They are, by kind of all accounts, the most advanced in terms of their performance, and I would say their scalability. And the reason is that the qubits in these natural qubit platforms, they're already made for us. There is no fabrication. An atom is an atom. A particular isotope of a particular element is the same in Seoul as it is in New York City, exactly the same. So if you need to make 10,000 of them, it's easy to do that because they're exactly the same. They're already standards. So I would claim that these natural and synthetic platforms, it's wonderful research on all fronts. But I think the synthetic platforms, there's a lot more science needed in understanding how these systems scale. Surfaces need to be perfect. There can be no defects. And if there are defects, how much do they affect things? And there's a lot of science needed to understand how we can get them together without noise and so forth. The natural platforms, I don't think they need as much science. They need a lot of engineering. We need to control these systems. How do you control a single atom isolated from the world? Well, that's largely an engineering problem. It's a control problem. The quantum system is already done. It's an atom. We don't have to assemble the quantum system. So there are different challenges in these platforms, and I think it's great for government laboratories, universities, and industry to play in all of these platforms. I think these natural platforms probably demand more of an industrial approach because they need more engineering, and these probably require more of an academic approach because they need more science. Now, you may have thought this was the other way around. I mean, if you're going to build a silicon quantum computer, that's engineering, right? No. It's science. It's fundamental science. Nobody knows how to scale a silicon quantum computer right now. Okay. This is some more evidence over the last few decades of the error rates in two qubit gates, the controlled NOT gates, over time. And again, trapped ions had an early start in the 1990s, and now they're down to below 10 to the minus 3. This is the error rate per 2 qubit gate. Superconductors may have plateaued, not sure, a little better than 99%. Neutral atoms are coming down strong. It's not clear how far they'll go down. And again, these are all these are all published results. And again, one message I want you to go home with is that this error rate is actually very important. It implies how many gates you can perform before things fall apart. And if you can get down to 10 to the minus 4, that means you can roughly run about 10,000 operations. And that is something that you can't simulate using a classical computer. And I think that later this week you'll hear more about kind of the limits and where computation becomes hard. So now let me finally kind of wrap up by talking about the trapped ion platform, and Jungsang will tell you much more about that. But this is a so-called ion trap. This chip was built at Sandia. I have another one here. This is the IonQ version. It's just it's nothing. It looks real fancy and shiny, but there's nothing quantum about it. These are just a bunch of electrodes. Can't tell here, but there are about 100 electrodes here that have wires on the back of this chip. What's exotic here is that when this chip is put in a small vacuum chamber, no air, we can trap individual atoms on top of the chip. This is a crystal of exactly 80 atoms, the little blue dots. Each of them is a single ytterbium ion of isotope 171. They're all exactly the same. And they occupy a space of about 0.5 millimeter. It's been blown up for the picture here. And they're resting about a 1/10 of a millimeter above that chip. The reason the chip looks like a bow tie is that we send laser beams through the side to control our qubits. So this is a pretty weird platform for a computer, I would say. Individual atoms, a vacuum chamber, laser beams as switches, but it works. It's very clean. Laser beams in particular are really interesting wires because you can turn them on and off. You can reconfigure them. Real wires are a no-go. If you have a real wire connecting to your qubit, you might as well go home because a real wire is not quantum. And it's very hard to make a real wire quantum. It has a surface. It has noise. It has to be at 0 Kelvin, near absolute zero. So very hard to think about that. The wires we use in this platform are beams of light, and they have a very light touch. Now, each atom here, why is it glowing? You're not used to seeing single atoms, but we can do this because there's nothing else there. There's no background. And we're shining laser light that causes this atom to fluoresce strongly. We understand the electronics of a single atom very well. And inside that atom are 2 energy levels. We sometimes call it a spin. But these 2 levels we use to store a qubit, a quantum bit. By the way, these 2 levels are exactly the same type of levels that are used to define time. These are individual atomic clocks, in fact. And ytterbium 171 is a particularly good clock, and that's why we can spell out the energy splitting between those 2 levels to, 10 or 11 digits. And they're all exactly the same. There's no calibration needed there, okay? So this is the platform, and the atoms interact because they're not neutral, they're charged. And so that's why they form this crystal. That's why they're not forced together in the trap. They repel each other, and that equilibrium that compromise gives this type of a crystalline structure, and their separation is a few microns, and we can optically resolve them. So this next slide is a little technical, but how do we do a gate? How do we execute a controlled NOT gate or an entangling gate between two ions? Well, we simply aim laser beams on the two ions in question, and the laser beam applies a force to the ions. It actually pushes them around a tiny bit, just a few nanometers actually, compared to the many micron spacing. So this drawing's exaggerated. And the key point here is that force, the direction of the force, depends on the qubit state. If the qubit is in one particular state, it goes up in space. If it's in the other state, it goes down. And the point here, I'll just skip to the truth table here. The point here is that if both atoms are in the same state, they will both move up together or down together. Their separation is exactly the same. Their charge, their Coulomb repulsion is exactly the same. But if they're in the odd state, 0, 1, or 1, 0, then they move in opposite ways. They're a little further apart. And because they're a little further apart, these two states suffer a small phase shift. This is the simplest application of the Schrödinger equation. This is H, our control field. And when we set that phase to be pi over 2, it turns out this is as expressive as a C0 gate. It's a gate that we can use for computing. So this was pointed out a long time ago by Sirac and Zoller in the mid-90s, that you might build a quantum computer based on trapped ions. It was refined by Mollmer and Sorensen, and this is really the gate that we all use now, the Mollmer and Sorensen gate, the 2-qubit gate that we build algorithms with. And so this is a schematic of what an ion-trapped quantum computer looks like. We have a bunch of laser beams. There's a lot of optical engineering here. A bunch of laser beams, one beam per atom. And again, there's a lot of technical information here. I won't get into that. But there is a kind of a cool little video here I have that I want to show you. Okay. Up here is a quantum circuit. It's a space-time diagram. We have 7 qubits. This is a circuit, and we're going time from left to right. These boxes are denoting interactions between the qubits in question. And we start by initializing them in the state 0. And we can do that with a particular laser beam. They're all initialized in the state 0. And then we run these gates. So between those two ions, between this ion, just that ion, and maybe 4 at a time, just one, like a square root of NOT gate if you want. C0 gate, another rotation, a couple of gates here. So this is the algorithm, the structure of these gates. And you can see when the ions are getting fuzzed out when we apply those gates. That's the force. And then my favorite part, at the end, we measure the qubits by simply shining a laser beam on them all. And if the atom is in the state 1, it glows. If it's in the state 0, it's dark. So you look at the fluorescence on a camera, and you can read out your quantum state. So that's it. So this is sort of a high-level picture of an ion-trap quantum processor. And the bad news is this is what it looks like in the lab. So this is a picture, actually this is my laboratory about 10 years ago at the University of Maryland. And there's no, I can't blame companies that build computers when they come to a lab like this and they're horrified. Oh, this is what the computer looks like? And that's only 3 qubits? So of course what's going on here is that we have an optical controller. We have a bunch of graduate students, and everything is super flexible. And Jungsang and I went on a long journey starting in about 2014 where we engineered this system so that almost everything you see in this picture here on the left is inside this black box. Everything we need to adjust can be done remotely and even at home in some cases. In fact, this project, it's a university project. It was funded by the US government at very high levels that allowed us to contract with companies to give us lasers and optical controllers that would allow us to really shrink things down and make things much more automatic. And as Jungsang and some of our engineering friends in optics say, if you know what you want to do, you can freeze it and make it small and better performing. And in Jungsang's lab, remarkably, he's even shrunk the vacuum chamber down to be the size of a deck of cards. And it's sealed right on the chip itself. So a vacuum's pretty exotic. You might think of it as a big vacuum chamber. like doing space physics, but no, it can be very small, and there's windows here where we can shine the laser beams in and so forth. I think I'll kind of skip over this. So we've at the university, we've used these quantum computers to do all kinds of experiments that are quantum simulations. And this one is it's like Shor's algorithm light with very small numbers. I won't get into the details there. Let me just move on and talk about IonQ, of course. This story of building that box at the university, it clearly needs an industrial perspective where we can make prototypes and improve them, making a few every year instead of one every 5 years. So, this type of operation is not really suited for a university lab. And so, of course, Jungsang and I founded IonQ in 2015, and things went super fast every single year of its existence, especially 2 years ago when the company went public on the New York Stock Exchange. And the amount of funding the U.S. government and private industry has put into trapped ion technology is astounding. It's huge. It's really large. So as Jungsang likes to say, when you get to $1 billion, you're really talking about something. This can be a technology that can be developed to solve real problems and get used. This is a nice example of sort of the engineering prowess at IonQ. This is a micrograph of the same ion trap I showed you before. We load ions one at a time from this loading zone, and we told the computer to load 24 qubits exactly, and the imager waits until we get 24. You can see they're even zigzagged when we load them for technical reasons, one at a time. And then we straighten out the chain, refocus the optics, all kind of automatically, and now we're ready to go. We have a chain of qubits, and they sit here for a long time, anywhere from an hour to a few days in some systems, or even longer. We're not limited by that. And so the systems at IonQ we've built many generations of systems. Some of the earlier ones are on the commoditized cloud servers that you can get, and the latest ones, and you'll hear more about this later this week, I'm told this is even outdated data. I mentioned we're starting to close in at 10 to the minus 3 error rate, and this is the IonQ Forte system. Is our 6th generation quantum computer. And this is a crystal of 35 ions, and the central 31 of them are used in this project. Now, with 31 qubits, there are 465 possible pairs, and we ran the 2-qubit gate on all 465 pairs, and this is the histogram of the errors. What's interesting is so the error rate is roughly a few 10 to the minus 3, but what's interesting is we know the fundamental error rate is about a few 10, maybe one or a couple 10 to the minus 4. So why that's good news is that the errors that we're seeing are still above the known fundamental error rates having to do with laser scatter. And that means that we can engineer our way out of this mess. We can make the errors go down even by another order of magnitude. And that's the promise, and we're building more and more systems to do that. I assume Jungsang will talk a little more about algorithmic qubit number and some of the applications we've run recently. But I think I'll maybe just stop there. I do want to put one more slide up at the end, which is sort of an outlook slide on scaling in the long run. And so in quantum computing, you need lots of qubits, and you need lots of operations, and they have to go together. The more qubits you have, the more operations you're going to have to be able to use. And that's hard because it means that if you're limited by noise in your system, as you add qubits, the qubits have to be better and better as you add them. And so this plot here is the number of qubits and the number of operations you can apply. If you're in the red here, that means it's not so interesting, so you can simulate what's going on using a classical computer. If you're in the blue here, you're in great shape because you're probably hitting some applications that will make great value, like optimizations and so forth. And this involves error correction. I didn't have time to talk about that. But in between, as long as you get outside of the red, that looks very interesting. This is where I think early algorithms will be developed. And the good news is these prototypes we're building at the university and at IonQ, they're steadily marching above the red zone here. And we're starting to encroach upon this so-called treasure land. By the way, I borrowed this from my friend Hartmut Nevin at Google. He has other arrows on there. Many of the other technologies, as you add qubits and you go up here, you're actually going to the left because the qubits are getting noisier and noisier as you add them. So it's very important to keep in mind, as you add qubits, they have to get better. And this is sort of why I don't see how that can be done in solid state without new approaches into science. And my last little animation is that, unfortunately, factoring an interesting number is way the heck up here. That's a long way away. However, if we find an application in here that makes value, that will pay the way to scale our systems to an extent where we could think about doing this sooner rather than later. All right, with that note, I will quit and hand the floor to Jungsang.